So I'd like to just start off by introducing ourselves and why we're here. So we're from the ARM HPC Compiler and Tools team. We're not your usual ARM suspects at the LLVM Dev Conference. Most of us are new to the community. And as a team, we were formed a few years ago to begin supporting research and development on compiler extensions for supporting the SV architecture. Our mission since then has grown beyond that. And so now we provide the software support for ARM in HPC and server. We're here today to talk to you about the SV ARM architecture and how it affects optimizing compilers. We're here to present our extensions to LLVM and Clang to enable auto-vectorization and support for the SV vector extensions. And we're also going to give you a rationale for the design decisions we've made in the past few years. And finally, we want to get good feedback from you guys on how we can contribute our changes back to the community. So let's start off with introducing what SV is. SV stands for the Scalable Vector Extensions. And this is an extension to the ARM V8A architecture. And it gives you new features that we didn't have before, the headline ones being gather and scatter memory operations. And these are memory operations that allow you to vectorize non-predictable memory access patterns. We have lane predication. So this allows you to vectorize loops with control flow more efficiently by if converting them. We have predicate-driven loop control, which is a new way of controlling your vector loop's termination condition by using predication. And we'll talk about that more later. We have vector partitioning and calculation. And this is a feature that allows us to vectorize loops with data-dependent exits. So these are early exits. And we also have extended integer and floating point reductions as well. So I should say at this point that SV is not a replacement for advanced MD. It's targeting different markets. It's very much focused on HPC at the moment. And so we're not focused on using this vector extension for things like DSP or image processing. Now, we have a new vector extension. What's the vector length? Well, there is no preferred vector length. The VL, as we call it, is entirely implementation specific. This is a choice that each piece of hardware makes for itself, and this can range from a minimum of 1 to 8 bits up to a current limit of 2K bits. And this could be increased in future. We should make clear at this point that the vector length doesn't have to be a power of 2. It can increase in 1 to 8 bit increments. And because of this, we need a new way to program your vector unit, and we call this vector length agnostic programming. And this is a way of programming where you write your code independent of any assumptions about your vector length. Now, on the diagram on the right, you can see a simple example of an SV add instruction. This instruction is predicated and has 4 operands. The first operand, Z0, you can see, is a vector register. And the .d here specifies that we're dealing with 64-bit element types. P0 is our predicate register, and this controls which lanes are active and inactive. Our predicate registers contain 1 bit for each element in the vector counterpart. And the /m here signifies that the predication scheme we're using for this instruction is merging. And what merge predication means is that your instructions' inactive lanes retain their existing value. The other scheme we have is zeroing predication. And zeroing predication just means that your inactive lanes have 0 written to them. And the diagram you can see shows an example of this instruction. We can have 2 elements in the 1 to 8-bit VL. And as the VL increases to 256, 384, 512, and so on, your vector length increases. We can process more elements at the same time. But all of these different vector lengths use the exact same instruction encoding. So that's what we mean by vector length agnostic. As a result of this, there is actually no need to recompile your code when you're targeting an implementation with a different vector length. You can compile your code, run it on a 256-bit vector length machine, and take that exact same code and run it on a machine with 2K vectors, and the code should just work. Okay. Hello? Yeah. As you can imagine, this has extensive implications for loop optimizations, especially auto-vectorization. Now, SV has two different styles of vectorization. The first is what you're probably already familiar with, and we call that scalar induction variable controlled loops. And this is the way that the current LLVM loop vectorizer works. And this pre-computes the loop iteration count at runtime or statically if known. And this is basically just using the scalar induction variable to determine whether or not you finished executing your vector loop. And what SV allows us to do is to approach vectorization from a slightly different angle, and we call this predicate controlled loops. And in this style of vectorization, what we're doing is we're using the predicate registers to control when our loop terminates. And as a consequence, one of the benefits that this has is that in some cases, we can completely eliminate the scalar tail loop, which is normally used to process the remainder elements. Now, let's look at a simple SV example. Now, we've got some simple C code here, and this is a loop that goes from 0 to 22. And all we're doing is we're loading from an array B, and we're adding the induction variable and storing it to another array A. Now, let's have a look at what an SV code generation for this might look like. So this is the code to implement the previous example. So we've got two blocks here. The first block is the loop preheader, and the second block is the vector body. And we'll go through this line by line. So the first line is a move of 0 to x0, x8. And all that's doing is setting up your scalar induction variable. And this is should be fairly familiar to most of you. The second instruction is an index instruction. And this is an SV instruction that you give it a start value and an increment, and it just generates an arithmetic series and puts the result into a vector register. So this creates a counting vector, in this example going from 0, 1, 2, 3, 4, and so on until you reach your vector length. The next two lines, count W and mov, what they're doing is that they're creating a vector induction variable initialization and an increment. And the final two instructions in the loop preheader are setting up our entry predicate for our loop. So what we're doing is we're moving 22 into a scalar register. That's our loop termination condition, if you remember. And the while low instruction is an instruction that you give it a start and an end, and it will create a predicate for every element for which that condition is true. So we're counting from, in this case, 0 to W9, which is 22, and that will create our entry predicate. Now, let's look at the vector body. The first two instructions shouldn't be too strange. We've got a load, we've got an add, and we've got a store. And these are vector loads, vector add, vector store, but you'll see that these are predicated. So the second operand for these instructions is the P0 predicate that we set up on loop entry. And the loads and stores are contiguous but masked. So they only load elements for which their corresponding predicate element is active. Now, the next line, incw, is simply incrementing our scalar induction variable by our vector length. Remember that we don't know our vector length at compile time. So at runtime, this will increment the x8 register by whatever your vector length is on that machine. And finally, we've got another while low instruction. And this one is creating the predicate for our next vector iteration. So we're using the x8 register, which was our scalar induction variable. And we're going to create the next iteration's predicate value in P0. And one of the features of the while low instruction is that it sets the flags for us, these flags are the same condition code flags that we use for normal compare and branch, the NZCV register. And what that allows us to do is that we can reuse our existing branch instructions to decide when we want to branch back to the loop header. The while low instruction is going to do a test on the predicate, and then we're going to decide, okay, if our first element of the next iteration's predicate is active, that is, do we have more work to do? Branch back to the loop header. So that is what an SV vectorized loop would look like. Now, the next step is for us to show you exactly what we've done to LLVM to support this kind of vectorization. And Graham is going to talk about that now.
Thank you. So our goal is to take this C function and generate Can you hear me now? Yeah. Okay. So current LLVM IR cannot express this as it has no concept of scalable vectors. So let's start where we are with upstream LLVM today, see where we run into problems and how we can solve them. So we're just focusing on the vector body for now. And this is IR that you get for an ISO like neon. So the constant for an induction update isn't related to anything else in the loop. And you can identify as the vector factor when it's used for updating the induction phi, but if it was used somewhere else, then it may just actually be from the original source. So we want to tie it to something related to a vector type. So we've added a new instruction, element count, and the runtime value that gets generated from this will match the number of elements that's actually from the type of the input vector. So the second problem we encountered is that you can't really have constants because you don't know how many elements you have. We could, for now, stick in constants that match the maximum size of SV registers, but we want to be forwards compatible such that if we ever increase that maximum, we'd still run. And you'd also significantly expand your binary size if you stuck in constant tab large. So all the required cases can actually be handled by a simple numeric series. And to produce that series, we've added a new IR instruction, series vector, which, as Amara's earlier example shows, just basically starts with a given value and then increments every one past it with the step. And for all the cases we found, we can use this for shuffles like reversing, picking the high and low parts of a vector. We can do that. Interleaving is a bit more finicky, but we can do that with a few extra instructions. And this is very useful for gather and scatter strides. So with those problems taken care of, we now need to actually make it scalable. And to do that, we've changed vector type to, instead of just having elements, to have a struct with both a minimum number of elements and a flag indicating whether it's scalable or not. If it's not scalable, then minimum is exactly the same as what you have today. If it is, then it's the runtime number of elements is a multiple of that minimum. And for the textual formats, you just prepend NX. So why didn't we just do it as NX type? Why have the minimum? Well, it's hard to reason about the total size of the vector that way. You can't cast between vectors of different type sizes for the elements. Why didn't we make it an independent new type rather than changing vector type? Well, there's a lot of existing code that already works with this that doesn't care about the vector length and just cares about what the elements are doing. And we'd like to reuse all of that instead of duplicating it. Why didn't we add a new type inheriting from vector type? Because we didn't want to have multiple constructors and trying to pick between them and possibly dropping the scalable flag if it exists. So with that, we can now properly vectorize our initial example, but there's one major feature of the vectorizer that we haven't supported yet, and that's reductions. So the current approach in LLVM is to manually tree reduce in the vectorizer, and then pattern match at cogen and put in your horizontal reduction intrinsic. This doesn't work for SVE because we don't know how many elements we have, and it may not be a power of 2. So it would need a loop, and then you'd have to hope that nothing broke that loop in such a way that the optimization wouldn't be able to recognize it. So we use intrinsics, and you can ask the target info what the intrinsic for a given operation is. And we know that there's been several attempts to add this in the past, and they've always been rejected because you can pattern match it in the back end. Now we can't, so possibly now's the time to actually add them. So with this, we now basically reach parity with Neon in that you can vectorize a loop, and if you've got a full vector's worth, you process it in the vector body. Otherwise, you bail out to the scalar tail for all remaining elements. So that's the minimum level of SVE support we need, but we don't want to stop there because scalar tail has a much larger impact for larger vector sizes than it does for the smaller ones. If there's a high trip count, you don't care, but many of the HPC kernels that we've seen, they've heavily nested the loops 3 or 4 deep, and the innermost loop may not actually have that many iterations. So for a particularly bad example, if you're working on bytes and you have a 256 byte vector, then up to 255 elements would just go straight to the scalar tail. Whereas with Neon, all but the last 15 would be processed in the vector. So people implementing larger vectors shouldn't be penalized for doing so. Unfortunately, SVE features predication, as we've mentioned. Process less than a full vector's worth of data and mask out unused lanes. And we can use those predicates to control loop flow. So we add a new phi for your vector body, and it matches the induction phi, basically, to calculate the next value for it. You use a series vector from the next induction variable value, and you compare that against the splat of the trip count. With this, when you're not processing a full vector's worth of data necessarily, you may cause faults or corruption in memory by using normal loads and stores. So now all of them must be masked. And as mentioned earlier, we need to test the first element of the predicate to see whether we want to continue. So yeah, if you have a full vector, yeah, obviously you keep going. If you have a partial vector, you keep going, and it's only once you've actually finished everything that you stop. But there is a potential problem with this, in that if your trip count is very, very close to the maximum for the induction variable, you may actually wrap within the vector because you don't know how long your increment is. And that would ruin all of our careful work to avoid corrupting memory, because now you've got active lanes after your termination. It also means that you might not terminate at all, because for the next iteration, you've gone back down to the base of the induction variable type and you keep going. So we've added a new instruction called propff, and this searches across the predicates, and the first 0 it finds, the first false value, it will partition the predicates such that all lanes before the termination are active and all lanes from the termination point afterwards are inactive. So that handles wrapping within the predicate vector, but we need a second argument, the current predicate, in order to ensure that we terminate the loop. And basically, the current predicate is not all true. It effectively overrides whatever the value of the comparison for the next one is. It says, no, you're done, and you terminate the loop. So this instruction is the simplest form of partitioning instruction we could come up with. We would prefer a more advanced version, and we will send out documentation later describing what that might look like. So with these, we can now control the loop via predication.
So I just want to say a few words about compatibility. In the current loop vectorizer, we are now using element count and series vector for all targets. But the loop vectorizer's output isn't actually changed for all. The way we've implemented this is in that in IR Builder, when you have a fixed length vector target, element count and series vector reduce down in constant. That way, can make use of our instruction, but the resulting code should be the same. We've also added a new create empty loop method within the loop vectorizer. And this is the method that we use in order to use our predicate-driven loop control. It's in this method that we generate the test and prop FF instructions. But we could merge these into the current create empty loop, but we've kept it separate for now. And all of the existing reduction code for fixed length vector targets have been kept. But as we've mentioned, since we definitely need reduction intrinsics for SVE, this is an opportunity for all targets to perhaps canonicalize around reduction intrinsics in the loop vectorizer as well. Now, we've gone through the IR changes. The next major change area that we've introduced changes to is naturally code generation. So Graham's going to continue talking about that now.
We obviously need to mirror the IR scalable types in selection DAG. So for each existing vector MVT, we've added an equivalent scalable version. Since the minimum size of an SVE vector is 128 bytes, or bits, sorry, any type where the minimum element count times the size of the type is equivalent to that, directly mapped to SV data registers. And legalization for these basically works exactly the same way it does for fixed length vector architectures, except that when splitting, you need to do it in terms of the element count. So in terms of opcodes, for each new instruction that we've had to add an equivalent opcode. Build vector takes a set of constants, and we can't have that, so we've introduced splat vector as well. For shuffle vector with a non-constant mask, we've added vector shuffle var. And for insert and extract subvector for scalable types, the index is now a multiple of n rather than directly addressing a given element. With all of this, plus a pile of AH64 target changes, we can emit the code that we showed at the beginning. But we haven't just spent the last 2 years supporting this. We've also improved vectorized codes and removed some of the obstacles we found to vectorization. So for scalar evolution, we found several cases where no wrap flags were dropped, and we've gone as far as even disabling some optimizations to keep them there because it helps us generate much better code later on. For alias analysis, we've improved support for vectors of pointers, and we've taught capture tracking about mask loads and stores. We'd noticed that several loops had far too many aliasing checks, and it was due to us using the mask loads and stores for all loops. So after you vectorized your first loop in a function, all subsequent loops using similar pointers now had to plant far too many checks. For loop access analysis, we've added better support for strided access with non-unit strides. We've added size checking for invariant addresses rather than just assuming that they're zero size. And we've added a new bounds checking pass, which for loops that we've found where it seems like it should have vectorized, but the trip count had been held in a global or something, the uniform load had not been hoisted, Scalar evolution couldn't figure out what the trip count is, and we didn't vectorize. So this speculatively hoists that load out and then plants your normal versioning and aliasing skev checks. For the loop vectorizer itself, we have vectorization of all gaps, not just those used for gathering. This is because we really, really don't want to scalarize because it requires that we plant a new loop inside it. We have a better memory cost model for gather and scatter ops, which passes more details of what's going on to target info, such as the stride, so it can make better decisions as to what it will actually plant when it gets it. We vectorize some small mem sets that are present within loops, and we support ordered floating point reductions. And what are those? So your typical horizontal reduction instructions do not preserve the floating point semantics of a scalar loop. And that creates a barrier to vectorization unless fastmath flags are used to relax your constraints. This is not always an acceptable trade-off. So SVE provides additional reduction instructions which preserve the order of the operations in the scalar loop, and as such they must take a running total as a second input, and the reduction occurs inside the vector body. Going a bit further with predication, we've now started to tackle loops which have early exits, so breaks. And these are usually searching for a value and then terminating when they get it. If you have multiple exits, you need to resolve where your actual values for induction and reduction variables are outside the loop. And you also need to use some non-faulting loads, which don't fault when they go off the edge of a page boundary, to ensure that you're safe to vectorize things like strlen. This is still in the experimental phase, and we'd like to increase the number of loops and types of loops vectorized over the next year, including loops with multiple back edges. So we hope to prove this out and possibly push for inclusion later. So that's a brief overview of what we've done over the past 2 years, and now I'll hand back to Amara to tell you where we plan to go from.
As you can imagine, we've got quite a large diff, and naturally our highest priority at this moment in time is trying to get all these changes upstream. And assuming that our design decisions are accepted at a high level, this is our basic plan for upstreaming. The foundation for all of this is our changes to the IR type system. So once we get those changes into LLVM, it's then we can start to upstream our new IR instructions or intrinsics. And in parallel, we can also start to upstream our changes to the MC layer and the target backend. And once we have those two, then we can start to contribute our changes to the loop vectorizer and analysis. And we also have an ACLE intrinsics implementation in Clang and LLVM that we can also begin to upstream. So all of our changes are now available today. What we've done is we've published a GitHub branch, which is all of our changes in a single commit relative to our baseline community level, which is back in June this year. And it's hoped that this public branch will serve as a reference when we're having our discussions on the mailing lists about how to proceed forward. The code should be buildable, and we have LLVM at the moment. We don't have Clang just yet. So how can we help each other from here on? Well, although we want to upstream, there are also a number of issues that we need the help of the community to begin proceeding forward on. These are things like predicated floating point operations. And we think we need these because at the moment, the way the predication works in the loop vectorizer is that we do an entire vector FP divide, for example, and then we do a select afterwards to select the lanes that we want. And this doesn't preserve the exception semantics. So we think we need some kind of predicated FP instruction or intrinsic, or some kind of way to preserve these semantics while also vectorizing with predication. loop strength reduce. This is a pass that causes a lot of problems for generating efficient addressing mode code. We have a pass that does some of loop strength reduce, but we know that's not an ideal solution. We'd really like to talk to the people who know a lot about LSR and how it works internally in order to find out how we can best proceed forward on this, because it's really not a good fit for the way SV works. Now that we definitely need reduction intrinsics, we think now we can start to talk with the community about perhaps a generic reduction intrinsic scheme and what that might look like. And finally, as a result of the search loop vectorizer work, we've split out the loop vectorization legality parts from loop vectorizer into its own separate class. And we'd like to talk about perhaps a new API to allow these analyses to be used in other places in LLVM. So with that, I'd like to summarize what we've talked about today. SV allows a broader class of loops to be vectorized and allows us to extract more parallelism from sequential code. And we've introduced a bunch of new features to the LLVM IR in order to support this. We have a few additional links that you can look at if you want. We have a blog post from one of our architects explaining the SV architecture in more detail. And we have a white paper written showing you how you can use vector length agnostic programming in order to take advantage of SV. And with that, we'd like to take questions.
Questions? State your name to start.
Hi, this is Mario Guerra from Qualcomm. So I think this is cool. I'm curious, you said that the vectorization, I got the impression that it was hardware dependent. So does that allow somebody to decide what level of vectorization they want to implement in the hardware? Is that the goal of SVE?
Yeah. So however big a vector unit you want, that's what you can implement. And then the code will just run on it without modification and take advantages of however many lanes you actually have in your hardware. And the way that SV works is that higher privilege levels can have a larger vector length than lower privilege levels. So, for example, higher exception level can restrict the vector length of the lower exception privilege level. So, one of the possible uses is if you want to, if you validated your software works on a particular vector length and you want to be absolutely sure that it's running within the same environment, or perhaps for some VL-specific performance tuning. There are more than one use case.
All right, so assume we have the loop, then you have a function call inside the loop. Today, with the loop vectorizer in the LLVM loop vectorizer, essentially, if we don't know if we have a vector version of this function, right? We just emulate the, let's say, assume the vector, because at this point, we know the the vector length, assume is a 4. Then we can emulate the calling the scalar function 4 times. But with this scalable way, essentially we have to generate a loop to emulate the, let's say, because n is unknown at the compile time, right?
Yeah.
So then now at the code generation pass, or is there any way in the SVE you can give this n back to the, because this is a scalar, becomes a scalar,
so the way that...
Oh, this is Xinming from Intel.
Okay, so the way that we've actually handled this is that for things like math functions, sine, cos, what we have are nx, v, whatever intrinsics support. And these intrinsics are emitted by the vectorizer. And then we have a pass in our AX64 backend, which will basically expand these intrinsics into efficient SV loops, just like you said. But these loops take advantage of some SV-specific instructions that allow us to very efficiently basically walk through a vector one element at a time and scalarize it this way. But yeah, so using a loop is basically one way that we have to deal with this kind of thing. Yeah.
For the math library, you can have your own vector version. You can do a lot of things. But for the user-defined function, if the user marked as a pure function, we know has no side effect, right?
Yeah.
The automatic vectorization can still kick in. But at that time, since you don't have a library for it, you don't know what is going on. That's what I was wondering how you can handle that.
So yeah, we do for the math function case. We are calling the scalar sine cos. We're just doing it within the loop. I don't see any reason why our approach wouldn't work for user-defined functions if we know they're pure.
Oh, Junie for Intel. So under this SVE architecture, I wonder how you handle loop unrolling. So let's say, especially complete loop unrolling. So let's say I have a loop with a long chip count, and then after the loop is vectorized, then I can complete another loop. So now you have the the vector length is not fixed. So how do you complete another loop?
Did you understand?
So that was the unrolling. It's basically you use chained prop FS, so you have to propagate between one part of your unroll and the next, and then again when you're actually constructing your predicate for the next iteration. So you basically need multiple predicates, one for each part of your unroll factor.
So
you SLP type stuff? Yeah, we haven't tackled that yet. So,
I mean, SV does allow us to generate predicate patterns for specific vector lengths, and that's potentially one route that we could explore. But we haven't really focused on anything like SLP. Everything so far has been completely vector length agnostic.
All right, thank you very much.
Great. Thanks, guys.